Hi everyone, this is Ben Dichter, and I'll be walking you through the tutorial for creating extracellular electrophysiology data using MatNWB. So for this tutorial, we're going to be walking you through a fake hypothetical extracellular electrophysiology experiment on a freely moving animal. So the types of data we're going to show you how to convert are one, the subject information such as the species, strain, age, etc. of the animal. Two is animal position, so this could be their position in a real maze, but this would also equally apply to position in a virtual maze. Also trials that the animal is going through and metadata associated with those trials. Also the local field potential of the electrodes recorded during the experiment, as well as spike times that are recorded during the experiment. So I know that a lot of you are going to use these types, but also a lot of you are going to need additional types. We're just going through these basics here, but I assure you NWB has lots of different data types, and I will direct you at the end towards documentation you can use to find the data types that would be relevant for your specific use case. Okay, so first things first, we need to install MatNWB. So the way to do that is, I have this code commented out here because I already have this installed on my computer, but if you haven't installed it, then you're going to want to go ahead and uncomment this out and run this cell. So the first thing that this does is clones all of the code from the GitHub repository, then changes directories into the code that you just downloaded, and then this cell here recursively adds all of the directories that you just downloaded that are now in your working directory to your path. So these steps, if you're an experienced MATLAB user, you'll probably be used to these steps, but this one might look different to you. So, and this gets into how MatNWB really works. So the way MatNWB works is it reads the schema, the NWB schema describing how all of these data types relate to each other, and automatically generates MATLAB API code. It actually writes MATLAB code based on that schema. So this is the command that you need to enter and run to automatically generate all of those classes. It should only take a second or two to run, and you should be good to go. If you don't run it, then you won't have a lot of the classes that we'll be using in this tutorial. And if you're having trouble, if this throws an error on you, you might want to try making sure that you are in the MatNWB folder as your working directory. Sometimes that can fix some problems. If you do that, you should be good to go. Okay, so the first thing that we're going to do here is create our NWB file object. So this is the root object that's going to contain all of the data that we'll be converting. And in the constructor of this class, we enter a lot of the data that's just session level information. And basically all of the classes in MatNWB use this format of key value pair. So this is the key, the session description, and then the value that we're going to set for that key is mouse in open exploration. NWB file has 3 required keys: the session description, the identifier key, and the session start time. The first 2 are open text fields. You can enter any text that you want. The third one is a date time, which indicates the exact time to the second, if you know it, of the start of the experiment. And then there are a number of optional keys that you can choose to add, such as information about the experimenter, the session ID, the institution, related publications. You'll notice that there's this general prefix, and you'll notice throughout the tutorial there might be some prefixes. This has to do with the structure of the resulting NWB file. In the resulting NWB file, the experimenter field will be in the general group. You don't really have to worry too much about it, but just follow the lead of the tutorial and you should be fine. Okay, So this, if we run this cell, what we end up with is an NWB file object. And if you run this without the semicolon, or if you just run NWB at the end, then you'll see a nice printout that can already show you the data that's already in this, the NWB version we're using, as well as the institution, etc., that we've already added to the file, as well as a number of blank categories that we'll be filling in throughout the tutorial. So next we're going to be adding information about the subject. This structure can store information such as the age, the species of the subject, genotype, sex, and the required field here is subject ID. And you can also add in a number of other fields if you know that information. All of these fields, every single one of them is open text, and you can enter any text you want and it will be a valid NWB file. But we do have some recommendations that will help you leverage some of the automatic tools that are being created around NWB. So our first recommendation is that your age be in ISO 8601 duration format. So for this, you could have just said 90 days, and that would be valid NWB. But instead, we're here using this official format, which is P, which stands for period, which indicates that this is a duration, 90, and then D, which indicates a period of 90 days. And that is, that's what we're using for age. Description is free form. Species, we would recommend using the Latin binomial name. So instead of saying mouse, we would recommend mus musculus. Instead of saying human, we would recommend that you use Homo sapiens. This again ensures that you're interoperable across other data sets that have been posted that may have come from a lab that has a different primary language other than English. And we also recommend that for sex you use F, M, U, or O for female, male, unknown, which is often the case if you're converting old data particularly, and other if you have some sex category that doesn't clearly fall into male or female. So once you've created this subject object, you can then add it to the NWB file by setting this attribute general subject to the subject object that you just created. So I'll just go ahead and run this cell. And here you can see a nice little printout of the subject as well, which indicates the variables that we've set. You can also see that there are some optional fields that we have not set, such as the date of birth, which you can specify if you instead of the age. Also the genotype and the weight of the animal. I'm going to add information about the spatial position of the animal over time. So NWB has a number of special data types for storing specific types of information. In order to store the position of the animal over time, you're going to need a spatial series and a position object. So spatial series is an example of a type of object that inherits or subclasses or extends from the time series class. And this is shown in this diagram. We're using this open arrow to indicate that spatial series extends from time series. And what that means is essentially that spatial series is a special case of a time series. And it also means that all of the attributes that are in time series are also in spatial series. So spatial series has a name, a description, data, which has the units of measurements of that data, such as meters, which it will be in this case. And it also has a way of representing the times of the samples. And you can represent these samples either using rate and starting time if you have regularly sampled data, or you can use timestamps if you have irregularly sampled data. So all of that holds true for the spatial series. And in addition to that, well, one is we specify that units are meters in this case, and we have an additional attribute, which is a free text field called reference frame, which tells you where the spatial series is where the point 0, 0 is for the spatial series. Now, these spatial series objects are going to go into a position object. The position object holds one or more spatial series objects and indicates, kind of labels those spatial series as position information. So I'm going to show you how to add this position and spatial series object to an NWB file. So first we're going to generate some position data information. So here we're just going to generate some data across a line just so we can put some arbitrary data in there. Then we're going to create our spatial series object using the spatial series constructor in types.core.spatialSeries. So again, using our key value pairs, we're going to put data as the position data we just created. Our reference frame, which is, we're making that 0, 0 is bottom left corner. And then here we're going to say we have irregularly sampled data. So we're going to, or at least potentially irregularly sampled data. And here we're going to just use this lin space as that data. We could have used the rate and starting time if we know that we're going to have regularly sampled data. Now that we have this spatial series time series object, we're going to add it to a position object using this code. We're going to create the position object using this constructor, and then we're going to say that the spatial series object is that is within this position object is going to be this object that we just created. Now NWB, and I'll run this code before I move forward. Okay. So again, you can see a nice printout of spatial series here, which shows that we've populated most of the fields, but again, there are some fields that are unpopulated, in particular this starting time and rate, which I said we were not using in this case. And then we can add that to position. Okay, so NWB differentiates between raw acquired data, which should never change, and processed data, which are the results of some processing algorithms that could change. So in this case, we're going to assume that the animal's position has been computed from a video tracking algorithm. So in that case, the video itself that you're recording, that would be your raw acquired data, but the point-by-point position which you're extracting from that video, that's the result of this pre-processing or processing of the video. So we're going to call that processed data. Since processed data is very diverse, NWB allows you to create multiple processing modules, which are like folders that help you organize different processing data according to the type of data it is, or maybe what algorithm it came from. So in this case, we're going to create a processing module called behavior and put the position object that we just created inside that processing module. So here we're creating this behavior module with a description that contains behavioral data. And here, since I didn't end this with a semicolon, you can see a nice little printout of this. Now I'm going to add the position data that we just created to the behavior module. And finally, I'm going to set the put this processing module into the NWB file by calling nwb.processing.set. This here is where we name this processing module behavior, and then we give it the value of this processing module that contains the position object that itself contains the spatial series data that we want to add to the NWB file. So I'll go ahead and run that. Okay, now that we have a little bit of data into the file, let's go ahead and export it and see how we can explore this file. So to export data into NWB, into the disk using NWB, you just call NWB export, take the NWB object that we've been creating throughout this tutorial, and then supply the file name that you'd like to write it to. So, so first we're going to show you how to inspect this data using MatNWB. So you can use the command NWB read, supply the file name of the file that we just created, and now we have an NWB object that looks a lot like our original NWB object, but this is the result of reading a file that's been saved. And so we can go into this, we can say NWB file.processing, get the behavior module, get the position object that we've stored in that behavior module, go to the spatial series, get the specific spatial series, and then we can see that this data has indeed been stored in the read NWB file. So this is one way of inspecting a file that you've written. Another way is to use a tool called HDF-View. So this is a tool that we don't maintain, it's maintained by the HDF group, but since the resulting file is an HDF5 file, you can read it with this tool and get a graphical depiction of what's in the file that you've created. So here we're going to do that same process of going, we're opening up this file that we've created, we're going into processing, behavioral, position, spatial series, and then you can see this data that we've saved into the file. I've selected this data set, which pulls up a little window where you can actually see the individual data that we've created and put into this. You can also see some metadata associated with the spatial series data set. And now let's talk about adding trial information. So trials are stored in an object called a time intervals object, which subclass is dynamic table. Dynamic tables are used to store tabular metadata throughout NWB. They're used in this case to store trials. They'll also come up again when we're storing information about electrodes and information about sorted units. They're really nice because they offer flexibility for tabular data because it allows you to have required columns, but it also allows you to have optional columns and custom columns. And I'm going to show you an example of that here. So here's the diagram again showing how all of these classes are related to each other. We have the dynamic table, and then the time intervals class extends dynamic table. So again, it means that all of the attributes that are present in the dynamic table class are also present for these intervals objects. And then trials is a specific instance of the time intervals table, which has to have the name trials just so we know that this is the trials table. Now with this, this little segment here indicates that you can have 0 or more optional columns that you can apply a custom name to and a custom description. What essentially this is going to create is a trial structure that looks like this, where you have an ID, which is just counting the rows, and then you have start times and stop times of the trials, and then you can add custom columns onto this. So this is kind of the another way of thinking about the data that are described by these classes. So what we're going to do here is create a custom column that we're calling correct, and we're going to give it Boolean values. So, so the way that you create this time intervals object, you have to specify the columns of the table. So we have start time, stop time, and correct. You have to specify the description. Here we're saying trial data and properties. You also have to create this ID column, which you create with types.hdmf common.element_identifiers, and you have to set the data field. Now, one thing that might be not as natural for MATLAB users is that this element identifiers object is 0 indexed. So it's counting up 3 elements, but it's starting at 0. So this would be 0, 1, 2. And this is for compatibility with Python. And then we are creating the start time, which is a vector data. Most of the columns, they're kind of a standard column structure, uses the vector data type. So this is in types.hdmf common.vector data. And here we're setting 0.1, 1.5, and 2.5 as the start times of the individual trials. Likewise, we're setting the stop times. So we create this vector data object again. We set the data to the stop times. And then we're also creating this correct field, which again is vector data, and we're setting the data to false, true, and false. And this demonstrates that you can have different data types. So this is Boolean, whereas before we were using float, and you can also use string data types here in a cell array if you want to. So the way that you add this trials table to the file is you say nwb.intervals_trials equals trials, and now it's added to the NWB file. So now let's move on to the actual extracellular electrophysiology data. So the idea behind NWB is to have within this one file all of the metadata that another experimenter would need to analyze the file. In order to store extracellular electrophysiology data like LFP and spike times, there's actually a lot of metadata that's required by MatNWB and that's required by PyNWB as well, or any NWB API, so that we can ensure that any secondary user of the file would have all the necessary metadata. So as part of that spirit, we're going to be required to create this electrodes table. Extracellular electrodes are stored in the electrodes table, which again inherits from this dynamic table class. Electrodes has several required fields: X, Y, Z, impedance, location, filtering, and electrodes group. So you'll see that in the diagram here. Again, this is a dynamic table, so we can have additional columns. It has all of these required groups. The group is actually a reference to an electrode group object, which we'll have to create. And then electrode group has a reference to a device, which we'll also have to create. So since this is a dynamic table, we can add metadata fields in addition to these fields, and here we're adding a label so we can give labels to our electrodes. And here we're also demonstrating a different way of creating a dynamic table, which is to create a MATLAB native table object, and then we have a utility called util.table2NWB, which converts this table object to a dynamic table that you can add to an NWB file. We are going to say that we have a recording that has 4 different shanks and has 3 channels per shank. We're going to first of all declare all of our required variables in the table, and then create our MATLAB table object with cell2 table. Then we need to create our device that we'll be linking to, and here we're entering a description and a manufacturer for this device. We're also giving it a device name, and then we're going to add the device to the file with nwb.generalDevices. We can set the device name equal to this object that we just created. Now we're also going to need a soft link to this file because that's what is used to create these references. And a soft link requires the path of the data in the resulting HDF5 file, which in this case is going to be /general/devices/device name. We're going to have to use this within the loop when we create our electrode groups. Now I'm going to iterate over the shanks and create, the first thing we're going to do is create a group for each shank. So we have this concept called electrode groups, which are generally used to specify things like shanks or electrode formations within a probe. So to create an electrode group, first we're going to specify the group name. We're using the number of the shank within the shank name to make sure that they have unique names. And then we're going to, within the NWB object, in the general extracellular ephys attribute, we're going to set this group name equal to an electrode group object, and that electrode group object is going to contain description, location, which is the location of this electrode group within the brain, so some brain area, and a link to the device. So here we're using that link that we created earlier within this group, within this for loop. Now we're also going to need an object view, which is another type of reference to this electrode group that we just created in order to do this reference connection of the diagram. So, so here we're creating that, that view of the object, that reference of the object, and then in a for loop for all of the electrodes within each shank, we're going to create a row of the table, and here this syntax appends this row to the table. So these values match up with the variables that we created in the beginning. So 5.3 is x, y is 1.5, z is 8.5. The impedance, we're storing it as nan, which you are allowed to do for any one of these values if you don't know it. Location is a string, so we're just going to say unknown. Filtering, also unknown. For the group, we're specifying this object view that we just created. And then label, which is the optional field that we've created, we're going to kind of create our own string for that. I mean, clearly here, I'm making the x, y, z positions of each electrode the same. Obviously, in real data, the x, y position, z position would be different for each electrode. So here I'm just running table just so we get a printout at the end of what this table looks like. And I'll show you that now. MATLAB has a nice rendering of this table object. And then I'm going to run this utility, table to NWB. I'm going to give it the name all electrodes, and then I'm going to add it to the NWB file by running nwb.general extracellular ephys _ electrodes is equal to this electrodes table, which is the dynamic table that we just created. So I'll run that cell, and there you go. Let's talk about adding voltage data to the NWB file. So voltage data is stored in an electrical series object, which is another example of a specialization of the time series class. So here you see in the diagram, this is time series you've seen before, and electrical series extends it very similarly to the spatial series object that we saw earlier. The difference is that here the units are fixed to volts, and there's the addition of this electrodes attribute. So the electrodes attribute is of type dynamic table region, which allows you to reference rows in the electrodes dynamic table. Electrodes is a required attribute, which means that electrodes is also required because it needs something to reference, which is why we went through the process of creating this electrodes dynamic table. We're now using that as the target of a reference of this dynamic table region. So in order to do that, first we create an object view of the electrodes table, and then we create a dynamic table region that takes 3 arguments: table, which here we're going to direct it to this object view, description, which in this case we're going to include all of the electrodes. But the nice thing about this feature is it allows you to have data sets of voltages that that can be attributed to subsets of the available electrodes. So for instance, if you recorded LFP data on only a subset of the electrodes and you threw out that data for the rest of the electrodes, you could use this structure to indicate specifically which electrodes your data corresponds to. But in this case, we are going to have it correspond to all of the available electrodes. And here we are using the 0 index again. So from our range is from 0 to the height of the table minus 1. And this transpose is needed to get it into the correct form. Now let's add the acquired voltage data into the NWB file. So this data is going to go in a neurodata type called an electrical series, which is another example of a neurodata type that extends from time series. So it's going to get all of the attributes of time series, and then it also defines data as having units volts, and it adds this new attribute called electrodes, which is of type dynamic table region. So we're going to use this dynamic table region that we just created, and again, this is going to map from the data values in electrical series to specific rows of the electrodes table. So now that we've done the hard part of creating this electrodes table, the adding the data to the NWB file of the actual voltage data is relatively easy. We just use the types.core.electrical series and assign that to an electrical series object. Here we're, instead of using timestamps to specify the time of each sample, we are assuming that we have a regularly sampled time series, which allows us to use starting time and rate. So here we're setting starting time to 0, and the syntax for rate is a little odd, but it's starting time rate just means the rate of the time series, and we're setting that to 30 kilohertz. We're just going to generate some random data with 12 electrodes and 3,000 time points. In the electrodes field, we're going to assign this electrode table region that we've already created, and then we're going to specify that the units of the data are in volts. Then after we create that object, you can just run nwb.acquisition.set. We're going to name it electrical series. You could technically name it anything you want, but this is the simplest thing to name it, and then we're going to assign this object to that place in acquisition. And this marks this electrical series as being the acquired voltage data. So in addition to that acquired data, you might also want to store local field potential LFP data. And what we're defining as that in this case is data that has been downsampled or filtered or in some way processed from the acquisition data that we also want to store in the NWB file. So in order to indicate that this is processed data and not acquired data, we're going to put it in processing and put it in a processing module. And so in that processing module, we're going to put an LFP object, and that LFP object is going to contain an electrical series. So we're using the same fundamental type here to hold the data. This electrical series is the same type that we used for acquisition. We are marking that it is processed and that it is LFP by putting it in this LFP object and then putting that LFP object in the processing module. So, just like before, we are creating an electrical series object using starting time, rate, data, using the same electrodes object and the same data units. Then we're creating this LFP object and assigning this electrical series to the LFP object. And then we're creating this processing module and assigning the LFP object to the processing module. And then finally, we can add the processing module itself. We're giving it the name ECEFIS, which is a convention. And we're adding that to the NWB file. So now we have an NWB file that has a processing module that contains an LFP object, that contains an electrical series object that has the data and the references to the electrodes where that data was recorded. And that's the best practice way of storing processed LFP data in an extracellular electrophysiology experiment. So spike times are stored in another type of dynamic table, although this is a subclass of the dynamic table called units. Units is in the location -units in the HDF5 file, and every row of the units table corresponds to a different isolated unit that's been sorted from the raw electrophysiology data. So first, we're going to generate some spike data. And I have this code here just to generate some simple spike data. What I've done here is I've iterated over shanks and over units, and I've generated some different number of spike times. Each of these elements of the cell array corresponds to a different unit, and each unit has a different number of spike times. So that's pretty important, actually, because when we create these columns, normally we would like to just create a matrix where the first dimension of it is the rows in our column. But in this case, with spike times, we can't just use a matrix. And if you're familiar with extracellular electrophysiology, you've probably run into this problem before, where it's kind of unclear how to represent these spike times in an efficient way. This is one way to represent it, where you have each of the units separated out in a cell array, but you couldn't easily put this into a matrix because with these cells storing times, you'll have a different length of each row of the matrix. So this is a problem that is a kind of a general problem in computer science that we call the ragged array problem, or a jagged array. And if you look down here, this is an illustration of an example of the types of data that you might want to fit into a matrix, but it doesn't quite fit into that form. Now, we have a special way of representing ragged arrays inside of a dynamic table, which is called the vector index. And this is how it works. So all of the data from all of the units is going to be in one column, in one data set. So here we have all of the data in green from unit 1, and then in purple from unit 2, and blue from unit 3, and so on. And then we have a second data set that stores indices into this data set. So this 6 indicates that the 0th unit goes from 0 to 5. This 9 indicates that the first unit goes from 6 to 8. This 11 indicates that this second unit goes from 9 to 10, and so on. So between these two data sets, you can represent an array which has an arbitrary length for each row, essentially. And we're going to use this to represent spike times. So the way that this is represented is you have a vector index array that targets the vector data array. And we have this utility function here, util.createIndexedColumn, which takes in a cell array like the one created above, and automatically it also requires the path of where you're planning on putting this data, which, because the units table, as I've set up here, the units table is in -units of the HDF5 file. So the data set that we are going to target here is -units.-spike times. And then the result here is this spike times vector. The spike times vector is the data here, and the spike times index is the data set that targets that data. Now that we have those data sets, we can create our units table. So this is another example of a dynamic table. So you can add more features to this if you want to, and we often see that people do add features corresponding to individual units. But in this simple case, I'm just going to do the minimal, which is to just include the spike times. So I'm just going to have one column. So my cell array is just a single element, which is spike times. And it requires a description. I'm just going to say units table. We have this IDs field, which I'm just going to indent this, which has one key value pair. The key is data. The value is indices spanning from 0 to the length of spikes -1. So that's a 0 index array, similarly to the other dynamic tables. And then we're going to take these objects that we created up here with our create index column, the spike times vector and the spike times index, and add those to this constructor, which gives us our units table. Okay, so that's all of the data that we wanted to put in. We had species-specific information, we had position information, trials, voltage traces, LFP, and the unit spike times. Now to export this, we're going to just call this NWB export function. I already have a file by this name. I don't think you should get this warning, but you shouldn't have to worry about it. Let's move on to reading the data. Again, to show you how to read the data, you can do NWB read. You put the file name in, and then you can traverse the hierarchy that we created in the first place to get to the data. But I also want to talk to you about how we read the numerical matrices that we've stored here. So if you just enter .data, .data, yeah, okay, you'll get a data stub object. You won't actually get the whole data matrix. The reason we do this is often the file itself is so large, there's so much data in an individual session that you don't want to load it all at once. So what we're providing here is an interface that allows you to lazily load the data. And by that I mean you're able to load only the segment of the data that you need at that time. So, but maybe you want to load all of the data. And so in order to load all of the data, you just say .load without any arguments, and we'll see printing out all of the data that we loaded in here, which in our case isn't very much, but in a real data set that that might not be something that you really want to do. Instead, you might want to access regions of the data. So, and to do that, you do the same command as above, but you put in additional arguments to the load command, and this just indexes the data. So if you wanted rows 1 through 5 and columns 1 through 10, then you could do load. This is row start, this is column start, this is row end, this is column end, and that will print out just a sub-region of the data from above. And this is one indexed, which you will be familiar with as a MATLAB user. So it doesn't start indexing from 0. You can do a similar lazy loading of data with the spike times, where you are often in a situation where you only want to read one of the units or a few of the unit spike times. You don't want to read all of the spike times at once. So we have this utility function, read index column, where you can input the spike times index object and the spike times object, which holds the data, and then you can say which of the units you want to read, and it will go in and fetch specifically the spike times for that unit. So running these here, you see the 5 by 10 matrix from this command, and you see here the spike times, which is length 16 for the first unit. And that, okay, there you go. So there you have it. There's how to write some of the basic data formats for extracellular electrophysiology and how to read them back into memory in order to do analyses on them. But there's much more. You can check out, if you're interested, other MATLAB tutorials. We have ones for calcium imaging and for intracellular electrophysiology. We also have tutorials in Python that I encourage you to check out if you know both languages. There are also some additional advanced write tool tutorials that we have in Python where you have really fine-grained control over how the data is represented in memory when you write it. And we also have a tutorial on how to build extensions, which allows you to capture types of data that aren't fully captured by the core schema. Additionally, I just want to point out where you can find kind of more information to move forward with extracellular electrophysiology in MATLAB. Here is the MatNWB repo on GitHub. And if you're having issues, I encourage you to raise issues here. Lawrence, the lead developer of this package, is really diligent about helping people through any issues they may be having. He's really great to work with, so I encourage you to just kind of file an issue if you think there might be a bug. I also want to draw your attention to the MatNWB API documentation, which provides a list of all of the neurodata types that are defined by the core schema and provides information about each one. So here, I'm just clicking on imaging plane for optical physiology. It describes all of the different fields that you can use to specify an imaging plane. One that might be more relevant here would be pupil tracking. That might be something you're doing. So you can see that pupil tracking contains a time series object. This is kind of similar to the position object. So if you have other types of data needs, I encourage you to look through this documentation first. But if you don't immediately find what you're looking for, please feel free to contact the NWB core development team or reach out on Slack, and we'll be happy to direct you to the types that are relevant for you. And if they don't currently exist, then we can help you create an extension for your specific needs. All right, so thanks for listening, and let me know if you have any comments or suggestions, or if you have any additional questions about this material.